Have you ever looked at a jet engine and just wondered, how on earth do engineers even begin to analyze the energy flowing through something that complex? It seems insanely complicated, right? But the secret, it actually boils down to one simple, incredibly powerful idea that'll change how you see the world. I mean, seriously, just think about it for a second. With all that energy and all that mass flowing through a power plant turbine, where do you even start? Where do you draw the line to begin your calculations? It feels a little like trying to measure a cloud, doesn't it?
Well, believe it or not, the answer is actually pretty elegant. It all starts by defining a system. That one little word is the key. It's what unlocks our ability to analyze and understand energy pretty much anywhere we see it.
Okay, so to make sense of all this, we use three basic building blocks. You've got the system itself, you've got the surroundings outside of it, and then you have the boundary that separates the two. Getting these three things straight is the absolute first step to analyzing, well, just about anything.
So, what is a system? It's really just the part of the universe we decide to focus on. That's it. It could be the coffee in your mug, the air in a tire, or the steam moving through a turbine. We're the ones who get to choose what's inside our imaginary box for studying. And what about everything else? Well, that's easy. We just call it the surroundings. So if our system is the coffee in your mug, the surroundings are the mug itself, the table it's on, the air in the room. You get the idea. Literally the rest of the universe. All right, now for the most important part of this puzzle, the boundary. This is the line, the surface, that separates our system from its surroundings. It defines what we're looking at. And here's where it gets really clever, because that line doesn't have to be a physical wall. A real boundary is easy to picture, right? It's the metal casing of an engine or the moving face of a piston. But, and this is the game changer, we can also just draw a totally imaginary boundary right in the middle of empty space. Think of it like drawing a box around the entrance and exit of a nozzle to analyze only what flows through that specific spot. So now that we have those definitions locked in, we can start putting things into categories. And the first major type of system we've got to understand is the closed system. The name really gives it away. A closed system has one simple, unbreakable rule. Mass can't get in and mass can't get out. We're studying a fixed amount of stuff. Now, energy, that's a different story. Energy, like heat or work, can totally cross the boundary, but the matter itself is trapped inside. The classic example here is a sealed, rigid tank. No matter how much you heat it up or cool it down, the amount of gas or liquid inside is exactly the same. Same goes for the gas trapped inside a piston cylinder. The boundary, the piston face, might move up and down, but the mass of the gas inside, it's constant. Okay, but what about all those things where stuff is constantly flowing through them? You know, like the turbines and compressors we talked about. For that, we need to talk about open systems, which we analyze using a really cool concept called a control volume. An open system is just a specific region in space that we decide to study, and its defining feature is that mass is always flowing across its boundary. This is the concept we need for just about every engine, pump, or nozzle you can think of. So let's just boil it down. The only real difference between a closed and an open system is mass flow. Closed system, no mass gets in or out. Open system, it does. But check out that last point because it's super important. In both cases, energy is always free to cross the boundary. See, with an open system, we don't try to follow a fixed chunk of matter as it moves around. That'd be kind of impossible. Instead, we just define a region in space, a box, and watch what happens inside it. That region, that box, is what engineers call a control volume. We're not tracking individual molecules, we're tracking a section of the pipe they all flow through. And, it just follows logically. A system has a boundary, so a control volume has what we call a control surface. It's the exact same idea, it's just the surface, real or imaginary, that encloses the region we're interested in. So, why do we care so much about these definitions? Well, because choosing the right type of system is the fundamental first step for analyzing almost every single machine that powers our world. Think about devices like compressors, turbines, and nozzles. They're all perfect examples of open systems, right? A fluid flows in, some work is done or extracted, and it flows out. The very first thing an engineer does to analyze one of these is draw that imaginary control surface right around the device. So the big takeaway here is this. Properly identifying your system as either closed or open is the most critical first step you can possibly take. It determines all the equations you're going to use, the assumptions you make, the whole shebang. Get this right, and you're already on your way. Now that you have this powerful new way of looking at the world, I want to leave you with a question. Just look around you. Your refrigerator, the radiator in your room, even your own body. Where else can you start to see these systems, these boundaries, and these surroundings just waiting to be analyzed? Something to think about. Thanks for tuning in.